We are looking at the surface area of pyramids and cones. And perhaps we'll see it's surprising that despite them seeming like cousins as far as shapes goes, as far as finding the surface area of each, they're quite different. So, I mean, the things that are the same about them is that they have a base and an upright surface, which goes on a slant. But, of course, the pyramid has flat surfaces that move upwards, and the cone has a curved surface. So let's look at those. The first one will be the easier one, and we're talking about the surface area of a pyramid. And perhaps the easiest way to establish the method is by looking at an example. Find the surface area of this square-based pyramid. So we can see here we're given a pyramid and it has a square base. 8 centimeters is the side length, and we have a slant height of 5 centimeters. So that's not the vertical, the perpendicular height. It is the slant height along the outside there, and you can see that it's marked likewise all the way around, as you would expect. So, looking at our definition of surface area, we have one square base plus 4 triangular faces. Those 4 triangles will be identical because we have a square-based pyramid. If we had a rectangular-based pyramid, we'd have 2 pairs of sides that might involve a little bit more work. So obviously it's pretty straightforward. The square base, we have 8 by 8 side by side, and when we come to calculate our total surface area soon, we'll see that's where the 8 by 8 came from. With the 4 triangular faces, we have been given the slant height, but it can be seen as the hypotenuse of a right-angled triangle if we bisect the triangular faces. You can see that dotted bisector line there called H, and we use Pythagoras' theorem, as we're familiar with, and it'd be a short side, so 25 takes 16, H squared is 9, and because we can only use positive values, H is positive 3 once we take the square root. So we then have 4 triangles. We have half base times the perpendicular height. So perpendicular height we just calculated. We have 8. Now the side length of the square base, of course, is the base length of each triangular face. So half times 8 times 3, we add that onto our square base, and we get 112 centimeters squared. So the only variations on that would be if you were given different information, such as maybe not the 5, maybe you might be given H possibly, and other variations. The most obvious one is a different shape base. You could have a triangular based pyramid called a tetrahedron, or you could have rectangular based pyramid, or you could even have some sort of polygon base too, like a hexagon or an octagon or a pentagon. Okay, now for the cone. So hopefully you can see that I have here a little cut out of paper here, a little sector. So what I've done is get the compass from a piece of paper and basically cut a slice out of it. So we've got a sector, alright, and we've got, hopefully you can see that where my finger is, we've got a capital A and a capital B. I'm naming the sector in regards to those 2 letters. I'm naming things about the sector in regard to A and B. And maybe you can see an S. I've made that radius there S. The reason why is that when we fold this up and we join A and B together on the end, so A and B, we're on each end, we join them together, we get a cone, we get the curved surface of a cone. Hopefully the light's good enough for you to see that there. But of course at the moment the bottom of it's open. And to close the bottom we need a circle. and we can put those together and we have a closed cone. We can calculate the surface area whether it's an open cone or a closed cone. Now, I'm hoping that you can see the blue circle that traces the circumference of the base. Alright, so I took the base off and I've traced the circumference in blue pen, and also I've traced around the base of the cone in blue because these match, they touch each other. Okay, so they're the same length. So when I unfold it, we have that blue line traced around the outside of that sector, not those two straight radii, however. So the radius of this sector is S, the slant height. So I've marked that in. So the slant height is there going up the side, and it's also the radius of the sector. So let's put all these things together. So by that I mean let's write a few of these things down. So we have a circular base, and the circular base has a radius r, and we have the circumference is 2 pi r for that circular base. 2 times pi times r. Now for the curved surface, we had arc A to B, or arc AB, and the arc length is theta over 360 times 2 pi. Now I would normally say r, but remember it wasn't, it was s. Okay, so that there is s, because when you fold it up it becomes a slant height. Okay, so I'm using s deliberately there because it's the slant height, which will be useful for us. That's s, and not r, because r has a different meaning. It's the radius. Okay, they're different lengths, radius of the base surface of the circle. Alright, so we know that the arc length AB is also the circumference of the circular part too. So we write that down, but arc AB also equals 2 pi r. So that means these two things here are equal to each other. So basically 2 pi r equals theta over 360 times 2 pi s. So we can do a bit of cancelling. Divide both sides by pi, you get 1. Divide both sides by 2, get another 1. Times by 1 makes no difference. So r equals pi on 360 times s. So if we go r divide by s, so we're dividing both sides by s, that isolates theta over 360. So theta over 360 can be replaced by r on s. So we can see there, we can replace that up there with this here, because these things are equal to each other. Now another more important thing we can do in terms of replacing it is the area of curved surface, which is one part of the surface area of the curved surface. So that's this. Okay, this here, our good old sector. Okay, so the area of the sector is theta over 360 times pi. Now we normally would say r squared, but remember we've got this s, it's the radius, remember. Now, and we're talking area this time, area, not the arc length like up there. So that'll be an s squared. It's a fraction of the area of a circle. And we can replace, like we said, r on s with, theta on 360 with r on s. Sub that in there. We can simplify that. And there's a factor of s that gets divided out there. And so we have pi r s. So the area of the curved surface is pi r s once we simplify it. So the total surface area of the cone, if it's a cone that has a base. So once we get the circle base and we added it to the curved surface, like so, we've got two parts that come together to make the total surface area. Okay, so it's pi r squared for the circle base plus pi r s for the curved surface, and that's basically there is the surface area of a closed cone. It is handy to factorize that. So if you have a look at the first and the second term, there is a common factor of pi times r, so that would leave r plus s. So factorized, we have that there. So that's your surface area of a closed cone. So make sure you take note of that. And there's a summary there. If you have a hollow cone, it's the same thing, except for obviously we don't have the circular part there. So some people call that a solid cone, but it's got to have that circular surface. Let's do an example to finish up. And just remember, you can also use the factorized form, pi r outside of r plus s or s plus r. This one's written as s plus r. It doesn't matter. You could swap the order of those two, you see, so it doesn't matter. So you normally see it as pi r outside of r plus s, but it's exactly the same. So just like that. Okay, example. Find the surface area of a solid cone. The base radius is 5 centimeters, the height is 12, and we are given different information, especially that height is 12. We're not given s. Okay, so we have to find s, and again we use Pythagoras' theorem to find s. So just be careful about what information is given. That is not s, that is height. So we use Pythagoras again to find s, and it'll be 13. Then we're ready to use the formula, and it's a direct substitution into the formula, and to one decimal place we get 282.7. Calculator steps are shown there, so you could round that up to 283 centimeters squared if you want to round it to the nearest whole number.